So now let's look at how you find area in the plane when you're in polar coordinates. Now the geometry of this is a bit different than Cartesian. So what I'd like to do is kind of look back at Cartesian area in the plane and look at the analog in polar. So we'll start off with two graphs here. In Cartesian, we might have some y equal f of x running from A to B. And when we think of area, there's something implied there. We're really talking about the area between two curves. One curve is the x-axis. One curve is y equal f of x. And then two curves here, x equal a and x equal b. So if I was to describe that region, that shaded region there is all points where the independent variable x is between two constants, right? That's kind of the key here, is we stop our independent variable between two constants and our dependent variable between these two curves. Y is between the x-axis, which is y equals 0, and the curve y equal f of x. And we generalized this where these were both curves, right? We looked at the area between two curves. That didn't change much. It changed what the heights of our rectangles were. But what was the geometry? Then if we just look at one piece, one little section of that would run from some x sub k minus 1 to some x sub k. And then you picked some point in between there to be the height. And so you had some c sub k in there that you evaluated the function at, kept things constant, and created a rectangle, right? The base here was, I'll write it up here, delta x sub k. And the height was whatever the function was at c sub k. So area for us was based on this product that was really representing the area of a rectangle. That's what the Riemann sum was. That little, I'll call it a sub k, the kth area. Approximation area was this times this. And the key is you take over some small range, some small change in the independent variable, you keep the dependent variable fixed. And the result is a rectangle, right? So that's the basis of Cartesian integral calculus there, right? So what would be the analog over here in polar? So say we have some curve here, r equal f of theta. So we want to run between two constant values of theta. So we're starting at some theta and ending at some theta. So call this starting angle alpha and this ending angle beta. And then we want everything between r equals 0 and r equal the function. So we've got the independent variable theta trapped between these two constants. Just like x, the independent variable in parametric, was between two constants. But it's rotational, right? So it's a sweep. We sweep out a little bit. And here we stayed between y equals 0, the dependent variable from 0 up to the function. So r from 0 out to the function. But what does that do? All that's going to be is this shading. So right away you can see the geometry is different, right? The region you get is not really analogous to a bunch of infinitely thin rectangles, right? Which is how this is fanning out. So we're going to have a different geometry for what happens there in that area. So let's go to this and see what is the analog when you let the independent variable vary just a little bit, but keep the dependent variable fixed. So let's just draw one piece of that Riemann sum. So you're going to have some little bit of theta. So some small change in your independence. So call that delta theta sub k. And then there's some function out here, a little piece of that function, let's say. Try and exaggerate it. And we are going to keep the r fixed by picking some of the function in between there, right? Just like we pick some value of the function in between here to be the height of our rectangles. So there's some value on here that we're going to pick. We'll keep r fixed. So when you fix r, though, what you get is a little bit of an arc of a circle, right? Because all the way through that theta sub k, we've kept the r fixed. So we get this pi piece, right? And so that pi piece is our analog to the rectangle over here in Cartesian. So, and let's label this radius here is fixed. And it's fixed at the function at some theta in between there, just like the height of the rectangle is just some value of the function in between there. So f at some theta. Well, actually, let's just use c sub k. C is a theta now, so it's OK. We'll just use c sub k. All right. So what is the area of that? We call that a sector. A little, as you sweep out a little bit of a circle, the area you get there describes a sector of a circle, or a pi piece. So what is that area? Well, it's just some portion of a circle, right? So what portion of a circle do we have? Well, if you went all the way around, the angle would be 2 pi. But we only have this much out of 2 pi. So the area there of our sector is this portion of a circle, this much angle out of 2 pi. That's how much of the circle we have. If we had the whole circle, the area would be pi r squared, right? And there's r, so it's pi r squared. That's a whole circle. And this is the fraction of a circle that we're taking, so there's the area of our sector. Now we can simplify this a little bit. The pi's would cancel. And just like over here, I think it's kind of natural to write the delta last. So we end up with 1/2 the function squared c sub k at delta theta sub k. OK, so what does that mean in terms of integral? So when you take this Riemann sum and then you let the norm of the partition go to 0, this area becomes the integral from a to b of f of x dx, right? So what happens over here is as we add all these little sectors up and let the norm of the partition go to 0, then the area here Well, we're calling those angles alpha and beta. And it's not just the function, right? It's not just the function. It's 1/2 the function squared. So that's our analog in polar. So be careful when you're asked to do area. Two things, really. One is that the formula is different, right? We've been doing this for so long that we're just used to taking the integral of the function to get area. But now it's integral of 1/2 the function squared. And what you're getting is different, right? It's qualitative difference here. This is everything interior to the curve means between the curve and the x-axis in Cartesian. Interior to the curve in polar means between the curve and the origin. So the shading, I'm intentionally sort of shading these different than how I shade these. I want those lines in my shading to sort of harken back to these sectors that it's really made up of in the Riemann sum. And I like this shading to sort of harken back to those rectangles. So I use that type of shading to remind myself what the underlying geometry is in that Riemann sum. So now we'll look at some examples of finding area with polar curves.